Hi everyone, welcome to Vedantu NEET English. I'm Diksha Ma'am, your chemistry master teacher. And everyone, today we are going to start a new chapter, that is structure of atom. So the DPP of some basic concepts of chemistry is in the description box. You will see that there, right? You have 15 questions in that, and I want all of you to complete all the 15 questions, right? So for structure of atom, right, we are going to start with discovery of electrons, protons, Thomson model, Rutherford model, all of these things. But before that, let me know in the chat box if you're ready for the class, if the energy is high, because I am going to teach you with the help of simulations, right? So what exactly are these simulations? Let me just show you that. Let me just show you that. Simulations like these. Okay. So, like this is your Thomson model, this is Rutherford model, this is the, we will actually define, wait a minute. Yes, we will talk about cathode ray, anode ray, and here we will talk about Millikan oil drop experiment, right? So, all these things will be, I'll be teaching you with the help of these animations because I know that you have never seen this. So, it's very difficult to imagine these things, right? So, the simulations will be in front of you so that the imagination becomes very easy for you, right? So you have done this chapter in class 9th as well. So many of you are in class 11th who are doing this for the first time. So many of you are droppers. So many of you are in class 12th who are doing this for revision, right? So all of these students, right, whatever is the purpose, this lecture is going to serve the purpose for sure, right? So let's talk about firstly atom, right? So guys, if you talk about atom, right, at this point, we know that matter, everything around us is matter. Anything that occupies space and has volume is matter, right? We have studied it before also. Now, this matter, for example, me, right? I'm made up of small atoms. You are made up of small atoms. This pen is made up of small atoms, and this dot has, wait a minute, this dot also have million trillions of atom. It is that small, right? So we can actually pick out an atom and see what is there in the atom, right? So for these discoveries, we actually did some experiments. The scientists did some experiments, and based on that, we have our total structure of atom, in which the subatomic particles are electrons, protons, and neutrons. And this is what we are going to discuss, right? So firstly, we'll discuss about protons and electrons. Then we'll discuss about neutrons, how they were discovered. Then we'll talk about how they are positioned in the atom with the help of two models. There are other models as well, like Bohr model, quantum number model. So the last two models are most important. But the thing is that model, maybe in one lecture we'll be able to do only one model, right? Or maybe in two lectures we'll be able to do one model, right? So it is very lengthy chapter. For that, you need to have patience to complete this chapter in detail, right? So starting with, before atom, you should know one thing about atom, that atom is actually, like, if you know this thing, it will clarify a lot of things in your head, that this is nucleus. Here you have neutrons and protons, and electrons are revolving around it, right? Okay, so if you know little bit of this thing, then you will be able to understand discovery of electron protons more clearly, right? So let's talk about firstly electrons, right? For that, you need to know what are these electrons. Give me a second. For that, you need to know what are these electrons. So guys, electrons is nothing but it is actually a fundamental particle from which atom is made up of, and they are revolving around the nucleus of an atom, right? That's what we know now, right? And its relative charge, its relative mass, all of that we'll discuss about, right? So let's talk about, but just remember that these electrons, Stoney named these electrons, and he said that these electrons are negatively charged. Now, how Stoney got an idea that electrons are negatively charged? In the first place, how he got to know that electrons are there in the atom, right? So there is at that time, no, these discharge tube experiments were very famous, like very famous. Everyone, like today we have AI, which is very famous, right? Everyone is trying to learn AI, right? Similarly, at that point, discharge tube experiments were very famous, right? So that's why everyone was trying to do that. So there is Crookes setup from which discharge tube experiments were done, right? So what happened here? Same kind of experiment is done, and that experiment is called cathode ray experiment. For that, you need to understand what is this cathode, what is this anode, right? See, in electrochemical cell, you will see something else in electrochemistry, because at that anode is negative. But in these discharge tube experiments, they take cathode as connected to the negative terminal and anode is connected to the positive terminal of the battery. Okay, so if you see this, this is the battery and to the negative terminal cathode is connected and to the positive terminal anode is connected. So we can say that in these kind of discharge tube experiment, cathode is negatively charged and anode is positively charged because they are connected to the respective terminal of the battery, right? Now, next thing is, guys, please focus here, right? Okay, and also do respond in the chat box as well, right? So now, if you see this here, right, this is the cathode ray. This is the cathode. This is the anode, right? So what he observed that, see, electrons are not visible to your eye, right? You can't see that electron is going on. You can't see, right? So to actually visualize that is there any ray passing, so what he did, he had this fluorescent screen over here. Now you will ask, ma'am, what is this fluorescent screen? See, fluorescence is actually a phenomena in which when any particle strikes on it, it glows, right? So similarly, fluorescent screen is a screen on which if any particle strikes, it will blink, it will glow. That is fluorescent screen, right? Now here we use a fluorescent screen of zinc sulfide, okay? Now what he saw, now till now what you are clear with, that ma'am there is this cathode, right? Ma'am there is this anode, right? And ma'am what is happening? This is the fluorescent screen, right? And now this thing is, this particular cylindrical thing that you are seeing here, this is discharge tube inside which the gas is kept. Which gas is kept? Any gas is kept, right? Any gas, right? You'll keep the gas here. But the condition is that the gas has to be at low pressure and very high voltage. Now you'll think that, ma'am, why it is so, right? The gas that you will have inside it is going to be at very low pressure and very high voltage, right? So this question also can be asked to you, that why it is so. So low pressure is kept so that there is no disturbance in actually understanding. See, if I am analyzing, let's say, million of students, right? So analyzing million of students will be very difficult for me, right? But if I'm analyzing, let's say, 1,000 students, let's say 2,000 students, what is the data? I'm trying to figure out that if they have this topic they like, this topic they don't like. So it will be easy for me to visualize that, right? So similarly here also, they said that too many atoms of gas will be difficult to understand, right? That what is exactly happening here. So less is the atoms, it will be easy to make some conclusion out of it, right? So less disturbance will be there in the inside the discharge tube. So that's why low pressure means less atoms you will have, right? Low pressure was kept here. That's why you will see there is a vacuum pump here. Can you see this is the vacuum pump which is taking out extra gas from this particular discharge tube, right? Now, it's not like you can just take out 5 atoms here. You can't do it like this. You will put a gas and then by vacuum pump, you will suck some gas out of this discharge tube, right? Now, next thing, guys, is going to be, firstly tell me if till now everything is clear to you or not. From cathode, anode, then there is this discharge tube. Now in this discharge tube, what you have is low pressure, but the voltage is very high. Can you tell me why? Voltage is very high, right? What is the reason behind this such high voltage? This high voltage is done so that, because now you know that this is the atom, now you know this is the atom, this is proton, this is electron. Now you know that. They knew that some particles are inside it. They even knew what are these particles. They knew some particles will be inside the atom. But we need to take out that particles from the atom. For that, we need to have very high energy. That's why very high potential is needed to ionize these atoms. Ionize means to take out electron from these. For example, you have helium. This is one electron, one proton. You take out one electron, it will be hydrogen positive, right? So I want to ionize this particular atom so that if it is made up of some ray, now we know that that is electron, right? But at that point, they don't know that it is, they didn't knew that it was electron. Only the thing that they knew was that some particle it is made up of, right? So that's why what they did, let's ionize it with putting high voltage here. So that was the reason to have low pressure and very, very high voltage, right? Now, once you have understood the setup, it's going to be very easy for you to understand cathode ray and anode ray experiment. Trust me on that, right? So let's see that. What is going to happen? So what he observed here, that some rays were coming out of this cathode. He don't know the reason behind that yet. He said that some rays are coming from the cathode. Now we know that anode is positive, cathode is negative, right? But ma'am, over here you have anode. How will it strike the ZNS screen? How will we feel the glow? So for that, what he did, he said that this is going to be perforated. That means this is going to have holes between it. Just like you have a simple sheet and you have holes in that sheet so that the particles can pass through it, right? So that is the hole, so that the alpha particles I'm saying, so that the rays that are coming from the cathode, they can pass through the anode and then they can strike on the zinc sulfide screen and a glow will be there, which will tell you that yes, there is some rays that are coming out of cathode, right? Because these rays are coming out of cathode, that's why these are called as cathode rays, right? Now, we know that, okay, these are coming out of cathode, that's why they are called cathode rays. Now, the next question is, ma'am, why they are negatively charged? How can you tell they are negatively charged? See, because this is cathode and they are getting attracted towards anode, which is a positive electrode, right? So that's why we can say that this actually is a negative ray, right? This is this cathode ray that is coming out of cathode that consists of negative particles. That's why it is getting attracted towards the anode, right? And hence after attraction, it is passing through the holes and then striking on the ZNS screen. So I'll just show you a kind of very near simulation to this, right? Not exact, but yes, kind of near, so that you're able to understand what is happening here, right? Okay, so let me see if you're able to see this or not, right? I don't, now though things are very blurry. Let's see this. Let's see this, you're able to see this or not. I think it's not visible to you, so let me just less brighten the screen. Okay, a minute. Okay, now can you see that what is happening here? This particular plate is connected to negative terminal. This is cathode. This particular is connected to the positive terminal, that is anode. Now, This hole, can you see this here? This hole, can you see this here? This is perforated anode, out of which some particles of this ray is passing, right? And now what is happening? Because it is there is gas involved here. This is the discharge tube. There is gas involved here. Some particles are coming from the cathode and then they are passing through this perforated, and because they are getting attracted, because they are negative particles, they are getting attracted towards this positive plate, right? So here what they have done is they have further experimented this with putting positive and negative plates, whether it is getting attracted to the positive or the negative. This is one of the properties of cathode rays, that when they are put in an electric field, this is actually an electric field with positive and negative plates, right? So whenever they are put in an electric field, they are attracted, these particles are getting attracted to the positive terminal of the positive of the electric field, that says that these particles are negatively charged. Okay, and if you ignore this part, if you put a ZNS screen here, it will strike here and the screen will glow. That is your cathode ray experiment, and this is the identification what is happening when they are under the influence of an electric field. They are getting attracted towards the positive side of the electric field, right? Okay, everybody? Clear, everyone? Let me know. Let me know if that is clear, right? Chalo. Now, let's talk about the next thing here. That is this is all that I have shown. This is cathode, this is anode, this is the zinc sulfide screen. These rays will strike here and you will get to know that there is some ray that is coming out of the cathode, right? Now, let's understand, like, this is the cathode. This is all the theory part that I have already taught you. That greenish glow on the perforated anode, fluorescent screen will be there. Low pressure, high temperature, all of these I have already told you, right? Now, let's see the properties of cathode rays, right? So, first property is that it will always and always cast a shadow, right? So, produce sharp shadow of the solid object in their path, suggesting that they travel in a straight line. So, this you must have learned in your earlier classes. Wait a minute. Yes. This you must have learned in your earlier classes, that whenever some particle is passing in a straight line, it is traveling in a straight line, that particle can have a sharp shadow. Now, when you put a wheel in front of these rays, like these rays are passing here, and when you put a wheel here, right, then what will happen? This is the wheel and this is the shadow that it is casting, right? So, can you see it is casting a proper shadow? So, that means this is actual experiment that we are doing, that not we scientists are doing, this is like actual experimental photo, right? So, because of this shadow here, we can analyze that these cathode rays are passing in a straight line here, right? Second is they behave similar to negative particles, right? So, that's why first is they are getting attracted to the positive terminal, right? That means they are behaving like the negative particle. Now, this I just showed you that how in electric field, right, they are attracted towards the positive part. So, that's how negative particle behaves. This tells us that these cathode rays are negatively charged. Next, they were named by Stoneley, right? Stoneley named them that these particles that are inside these cathode rays, these are electrons. Then they can make light paddle wheel placed in your path rotate, right? So, if you have, this is, let's say, cathode, this is anode, and let me see if you're able to see this or not. This is the wheel that you have, and this wheel will start rotating, right? To make anything rotate, to make anything go in motion, you need kinetic energy for that. This means that these particles, they possess kinetic energy and are material particles, right? They actually have some mass, they possess some kinetic energy. No matter the mass will be very small, but they have some mass, that's why they are able to rotate the wheel, right? Because of mass, they will have some kinetic energy, and that's the reason they will start rotating the wheel, right? Next is the ionized gas through which they travel, right? Now, what do you mean by that? So this means that, for example, uh, they have a very high energy, right? So that's why what will happen, ionized gas means, for example, this is a gas, right? So they have ability to take out electrons from this gas, right? They produce X-ray when they strike on a metallic target. So whenever they strike on a metallic target, they have the ability. So these all are the properties of electrons that they observed experimentally, that whenever they strike on a metallic surface, they will produce X-rays, right? Then the characteristics of cathode rays do not depend on material of the electrodes and nature of the gas. Now this is a very, very important thing, that which is very frequently asked, that they are not like that you change the gas, the electrons will start changing. Now I'll tell you the reason behind that. Now we know that, I'm telling the reason because now we know the structure of the atom. Now we know that neutrons and protons are inside the nucleus, and electrons are like free bird, right? They are rotating around the nucleus, right? So that's why you can take one electron, you can make M positive, you can take two electrons, you can make M2 positive, you can make three electrons, you can make M3 positive. So these electrons can be taken out individually, right? It's not like you will take a bunch of electrons. Let's say it's not like that you have nitrogen. Let's say you talk about nitrogen that is having 7 protons, 7 electrons. It's not like you'll have to take 7 electrons all together. They are not fixed in a locker. They are rotating, right? So that's why they are free. We can take one electron one by one, and that's why they have their individual identity. This is one electron, this is second electron, this is third electron. They are individual particles, right? So that's why when you change the gas, right, when you have oxygen gas, you have nitrogen gas, every single gas will have same electron. Number of electron can differ, but that doesn't depend what is the number of electron in an atom. Why? Because we can take electrons individually. From oxygen, I can take one electron. From nitrogen, I can take one electron. From helium, I can take one electron. And from these, if I take two electrons also, they will be one electron, two electron. Individually, I'll take two electrons. So they will become two different particles when I take them out. For example, let's talk about helium. When you take two electrons here, these two are individual particles that you will have. When you have nitrogen, when you have, let's say, 3 electrons, you take, these are the 3, wait a minute, you take 2 electrons. No. Let's talk about, this is about gaining now. So let's talk about Al. Okay, when you take out 3 electrons here, that I'll tell you in later classes, right? When you take out 3 electrons from here, so it is Al3 positive. These 3 electrons are 1, 2, 3 individual, right? Okay, understood? They don't go hand in hand, that we will go together. No, right? So that's why it doesn't matter what is the characteristics of this, do not depend on the material of the electrode or the nature of the gas present in the cathode ray experiment, right? Okay. So that was about the discovery of electron, students, right? Now let's talk about J.J. Thomson mass ratio. So this is not so much in detail in your syllabus, right? So what you have to remember is that J.J. Thomson, he did some experiment. What was the experiment? The experiment was like this. Wait a minute, let me just show you. The experiment was like this. He took the same experiment. It's just that he placed this under magnetic field, that is north-south pole magnetic field. He placed it under the electric field, right? This is the electric field, this is positive plate, this is the negative plate, right? So when you place it in a magnetic and electric field, there are some things that you will see. So what are these things? That when only electric field is applied, this I showed you with the experiment as well. If you see this, I showed you with the experiment as well, that this is how it looks, right? It is going towards the positive terminal. I think you are not able to see this at this point. It's okay, right? So I have shown you this before also, that how they are actually moving towards the positive plate, because these are negative particles, they will move towards the positive plate. So that's why they will strike here on the A point, right? Then point C is when you have only the magnetic field, right? Then these particles will move towards this and they will strike on only the C point, that is opposite of the electric field, right? Then third was, he observed that when both of them were applied, then they went straight, right? Or when none of it is applied, also then they went straight, right? So he did, this is just a general overview of the experiment that I am giving you. After doing this experiment, he was able to analyze few points here, that the charge to mass ratio, how he will find out. He was like, the extent of deviation of electrons from their path in the presence of electric and magnetic field depends upon how many things? Charge on the electron, mass of the particle, and the strength of magnetic electric field, right? So what he said, that depends upon this thing. So by like so many experiments, he answered that what is the E by M ratio. How we calculated it doesn't matter, right? For you, this was the maximum that you need to know about E by M ratio. But this particular value, you should definitely know that this is the E by M ratio of the electron. And does this E by M ratio depends upon the nature of gas? No, because for every gas, the electrons are individual, right? They don't come in packets of Lays, right? They are like, you have 1 kg of dal, right? You don't take it in a packet, right? You take it in a packet, but it's not like there's a packet of Lays which has fixed number of Lays there, right? You can say 1 kg, you can say half kg. This is how it looks, right? So I don't know if this example fits in, but all I want to say is that, for example, some best friend, they always go together, and some friends, they don't go together. They are together, but it's not like that they will always be like, hey, we will like hand in hand, we will go together, right? Will not distract here and there. Electrons are not like that. Electrons are like, bro, I'm individual person, right? I'll go alone. It's okay, right? We were living in the same room. We were living in oxygen, nitrogen, whatever. But when I'm out of that atom, I can go anywhere I want to. I don't need to hold your hand. This is what the mentality of electron, right? So now charge on electron. Now guys, we know the E by M ratio. If you're able to find the charge on the electron, can you find the mass on the electron? Yes, right? If E by M ratio, if you know the charge, you can easily find the mass. So now Millikan oil drop experiment will define how to find the charge on the electron. Now for this, what you have to understand, it's not like it will be too much in detail asked to you, nothing like that will be there. But a hint of what is happening in Millikan oil drop experiment is good for you, because statement based questions can be asked to you, not numerical based questions, okay? So let's talk about this. Millikan devised a method. First, you need to know the name of this. Millikan oil drop experiment was done. Students get confused, ma'am, was it charge or mass? He actually determined the charge on the electron. His experiment was telling the charge, because you know E by M ratio, that's why you were also able to calculate the mass. He did not tell us that what is the mass. He firstly told us that this is going to be the charge. Then you know the E by M ratio, calculate the mass. Understood? Right? Charge was the thing that he was focusing on. So now this is your Millikan oil drop experiment. Let me just show you this experiment model in reality. How does it look like, right? So this is, guys, how it will look like, right? This is how it will look like. So you can see this over here, right? This is another animation from where you can understand that how does it look like, right? Understood? Now, the same thing, what is inside here, I'll tell you, right? This is what is this? This is like a pump from where the I'll just tell you what things are traveling here. Chalo, firstly, let me just tell you what is exactly this thing, right? Okay, it will be like more clear to you. Let's talk about this plate here. See what is happening inside. This is the thing that is called atomizer. I'll tell you what exactly we do here. It's like in the match, right? Your favorite cricketer, be it Virat Kohli, MS Dhoni, whosoever is your favorite cricketer, he is catching the ball, right? Same way, here our cricketer is oil drops, okay? Oil drop is going to catch the X-rays here, right? Oil drop is going to catch the X-rays here. Now, based on the capability, oil drop can catch one X-ray, 2 X-ray, 3 X-ray, 4 X-ray, 5, 6, whatever, right? So now let us see this. We need oil drops, we need X-rays, right? So what we have from this atomizer, we are giving the oil drop in a spray form, right? So here in a spray form, we are giving the oil drops that I'll just make here like this. These are the oil drops that you will have, okay? Inside it, here we need X-rays. So that's why this is the source of X-ray from where X-ray is moving here. And this is actually going to be on this side. Now, the main work here is that this oil drop should travel from gravity through this hole. There will be a hole here from which the oil drop will travel. Okay, this oil drop will travel, and this is the oil drop. And from this particular position, you will drop the X-ray from this side, and this will catch the X-ray maybe 1, 2, 3, 4. The zoomed in version can be like this. This is the oil drop that you have. It may carry, like, for example, n number of electrons here, right, from the X-rays, right? This is what it is. Now, let me just draw it. Chalo, let's keep this thing only here. Okay? Now, let's understand these are the, now again I am repeating this. You need oil drop to catch this particular electron from the X-ray, right? So this atomizer is giving you the oil drops, and this is the X-ray electron that you have. And when they both are combining, this is the thing that you are forming here. Now, how do you calculate the charge here, and how this is actually a stable experiment? So see this thing. This is a plate which has a small hole here, right? And this is another plate. Okay. Now, if you see this here, this is the negative plate, this is the positive plate. Okay. Now, this was a negative, wait a minute. This is the positive plate, this is the negative plate, right? A kind of electric field is developed here. Now, if you see from this microscope, someone, you, me, we are watching here what is happening here, right? So he's like, what is happening here? Now, what he observed that this oil drop is stable. This oil drop is not going downwards. Now, this is the miracle. The oil drop is not going downwards. That's why this person who is actually observing it was able to understand this particular situation, right? So, why it is not moving down? Because of some static stability here. See, one is the electric field that is working here. Okay? Electric field, this is the electron. That's why electric field wants that this should go upwards, right? Okay, because this is negative. Oil drop is not negative, electron is negative. That's why it will be attracted towards the positive plate. It will go upwards. Gravity is saying that you should go downwards. So, experiment is set in such a manner that these two things will become equivalent to each other, right? And this particular oil drop is your stationary oil drop, right? So, now with this stationary oil drop, how do we do the calculation? So calculation is, if over this oil drop you have Q is the charge of this oil drop, N is the number of electrons that you have, and E is the charge on one electron, then you can easily calculate this. Now, ma'am, will he calculate this is 1 electron, 2 electron, 3 electron, 4 electron? No. What he observed that the overall charge here is always integral multiple of a constant. Let's say this charge were coming out to be x, then sometimes 2x, sometimes 3x, sometimes 20x, sometimes 2000x, right? So that means it is coming out to be multiple of one constant. He said that this constant is nothing but this is the charge on the electron, which if you have 2 electrons, it will be 2x. 3 electrons, it will be 3x. It has 2000 electrons, it will be 2000x. It will be million of electrons, it will be million x. Right? So according to that, it is an integral multiple of a constant term that is called charge on the electron. Right? So that's why we finalized. Guys, tell me if that is clear to you or not. This is Q, that is charge on the oil drop. Overall charge, right? This was done experimentally. Experimentally, he was checking what is the charge on this particular oil drop. So it was getting that constantly it is some integral multiple of one constant value, and that constant value is going to be the charge on the electron. So that's why we say that after calculation, it was always coming out to be Q is equals to Ne, where N can be 1, 2, 3, 4 and so on. That's why after doing the calculation, this constant was coming out to be this much. That is the charge on the electron, right? Now, you know the charge on the electron, you know E by M ratio. From that, what is E? What is E by M? That is nothing but mass. So, you can calculate the mass of the electron here. That is coming out to be 9.1 into 10 raised to power minus 31 kilograms. Right, everybody? Okay. So I tried my best so that I can simplify these things as simple as possible. Right? So now let's do this particular question here that says that which of the following statement is not correct about the characteristics of cathode rays? They start from cathode and move towards anode. They travel in a straight line in absence of external. See, they start from cathode and move towards anode. That is correct. They travel in a straight line in absence of external. Yes. The characteristics of cathode ray do not depend upon material of electrodes in cathode ray tube. Yes. Characteristics of depend upon nature of gas. No, they will not depend upon the nature of gas. So answer is 4 is the incorrect statement. That's why 4th is the correct answer here. Right? Now let's talk about proton. Yes, everyone? Now, let's talk about proton. Okay? So, for proton, what we need to understand here, that proton, see, that's why I was telling you the examples here. Right? If you talk about hydrogen, okay? Hydrogen has 1 electron, and here I am not even counting the neutron, okay? So, 1 electron, 1 proton, after subtraction of 1 electron, you will be left with hydrogen positive. Helium, it has 2 electron, 2 proton, after taking out 2 electron, it will be helium 2 positive. Lithium, after this is 3 electron, 3 proton, after taking out 3 electron, it will be lithium 3 positive. Now, the experiment was done, and what was the experiment that he did was the same thing, right? Experiment was same. It's just that now instead of having the fluorescent screen on the anode side, he had it on the cathode side. This was the fluorescent screen, right? And here you can see the glow on the fluorescent screen. This is the anode, Sorry, this is the cathode, this is the anode. Now this anode was perforated. Can you see? This particular anode was perforated. So I'll just, can you see? Wait a minute, guys. So sorry. Yes. So if you can see this here, this particular anode is cathode is now perforated, right? So where I should write cathode is now perforated, right? It will be opposite of what we did there. Cathode is perforated. What is perforated? That means it has now holes, right? Now see this thing. First, I'll tell you what is the experimental setup. Then I'll tell you what is the observation. Then I'll tell you why this is the observation. Okay. So this is now ZNS screen. This is perforated. That means now they are checking, is there any ray coming out of anode also? And surprisingly, it was yes. The ray was coming, just one thing differentiated, ZNS instead of this, it is here. Instead of this perforated, this is perforated. Everything else is same. And now they observed that some rays are also coming out of these anode, right? And he called these anode rays, these rays as anode rays or canal rays. Okay? Anode rays or canal rays because they were coming out of anode. Now, next question is, ma'am, do we order the atom that now you have to give electron, now you have to give the rays from cathode, or now you have to give the rays from anode? No. That means if I have a setup where I put that ZNS screen is here also, where I put that this anode is also now perforated, both are perforated, this is also perforated. Now both are perforated. So now can you observe one thing that, wait a minute, let me just draw with the, which pen? Blue pen? Orange pen. Okay. If I have this also perforated and here ZNS screen should be same. Okay. Too much technical I am going, right? Yes. Okay. Now can you see ZNS screen equal is there on both the sides. Anode is also perforated, cathode is also perforated. Now if you see here also you will see the blink because of the anode rays, right? Because anode rays are coming from the anode, and simultaneously you will see that blink, some rays are also coming out of this particular cathode, and here there also you can see the blink on the ZNS screen. That means it's not like when we have perforated anode, only cathode rays are coming. When we have perforated cathode, only anode rays are coming. Both the rays, cathode rays and anode rays, were always there, right? Even when we studied cathode ray experiment, in that also anode rays were there. It's just that we didn't notice it, right? Now, if I have ZNS screen on both, I'll see that both rays are coming here. Here also you will see a glow, here also you will see a glow. Here you will have anode rays and here you will have cathode rays. Okay. So that means they travel along with each other, right? In the opposite direction. Now the question is, ma'am, why we have these anode rays? So the observation that he made was that in cathode rays we discussed that it does not depend upon the nature of the gas. But these anode rays were depending upon the nature of the gas. Ma'am, why so? What is the reason? The reason lies here, right? Now understand that at this point, now we know that this proton is inside the nucleus. If you have hydrogen, proton will be here. If you have like, I'll draw here, so they have drawn simple that hydrogen is there, one proton, one electron. Hydride means two electron. Proton means only one electron. You take out one electron. That means here what we are doing, we are taking out one electron. Here we are giving one electron. Now see one thing. Can I take proton in the similar way? Can I take proton out of this side? No. You will never study in periodic classification. You will study ionization enthalpy. The energy for taking out the electron, not the proton. So proton you cannot take out, right? So proton is locked in a nucleus from which we can't take out proton. So one thing should be clear in your head, that proton is actually a gaseous ion only. I'll tell you how. See, proton means only proton should be there. So when you talk about this H positive, this is actually the proton. Is helium 2 positive proton? No. Helium 2 positive has 2 protons. Lithium has 3 protons. And you can't differentiate. They are best friends. They will always go together. In that they are locked in a room, they will always go together. Right? So that's why when you see for hydrogen, it is hydrogen positive, that is 1 proton. For helium 2 positive, it is 2 proton. For lithium 3 positive, it is 3 proton. And anode rays are not protons. Anode rays are gaseous ions. Anode rays are gaseous ions. These are after losing the electron, there is some gaseous ion that we are forming here. And anode rays positively charged with that gaseous ion. Yes, in case of hydrogen positive, it is proton. Because you are left with only 1 proton. But other gaseous ions are multiple of proton. 3 proton, 4 proton. Let's say you have a very high voltage. That's why we have a very high voltage, because we want to take out all the electrons from the atom. Let's say you have nitrogen, right? Wait a minute, let me draw it on the next page. Let's say you have nitrogen. You have 7 electrons, 7 proton. You take out all the 7 electrons, you'll be left with 7 proton. This is the multiple of proton. This is not a proton. That's why every single particle, if you use different gases, the gaseous sign will be different, right? So everything was different in using different gases, right? Because electron, if you take out 7 electrons, let's say when you're taking out 7 electrons, right? This is 7 protons. This is the process. So when you're taking 7 electrons, one is going here, other is going here, third is going here, fourth is here, fifth, sixth, seventh. They are making different, they have individualities because they were free in the atom as well. But this particular proton, it is in the nucleus with 7 proton. That's it. So it can't move by itself, that 1 proton is going here, other is going here, third. No. That's why these anode rays are not protons. These are protons only in case of hydrogen. In other cases, it is your gaseous ions. Okay. So that is the setup that I was telling you about, that this will happen, right? Now let's talk about the properties here. They travel in a straight line. They carry positive charge. They are made up of material particles. Same experiments he did there. Straight line, why? Because it is casting a shadow, right? So material particle, why? Because it is having kinetic energy. It can rotate a wheel. Same things. The mass of the particle consisting of anode rays is found to depend on the nature of gas. This is the very important thing, that it will depend upon what is the nature of gas. According to that, you will have gaseous ions. Either it will be proton or it will be multiple of proton, right? Charge to mass ratio is also found to be dependent on the gas taken. Their behavior in an electric and magnetic field is opposite to that of the electron. So when they are coming out, and here you have positive plate, negative, they will get attracted towards the negative plate. because they are positive. That's how their behavior is opposite. Okay, everyone. So this is the origin of anode rays that I told you. This is the knockout of electron, right? There, it's not like you are taking out proton. You are taking out electron, and after that, the left part that you have, that is your anode rays. That is the gaseous ions, right? Gaseous ions are your anode rays. Now, charge on proton was found to be opposite of charge of electron, right? Electron is here minus and here it will be plus 1.6 into 10 raised to minus 19 coulomb. And if you talk about the E by M ratio, that is found out to be this one, right? That is maximum value E by M ratio for any positive particle, right? Then after calculating, the mass was coming out to be this one, right? Now, calculations and all is not important for you. What is important for you here? That I have taught you, the concept is important and the values in the end is important. What is the charge, mass of electron, proton and neutron? Now, what is wrong about anode rays? Their E by M ratio is constant. Is it? Anode rays, they depend upon the gas, right? So clearly first is wrong. They are deflected by electric, yes. They are produced by ionization of molecules, yes. Their E by M ratio depends upon nature of gas, yes. So this particular thing is wrong. They are not at all constant. They are dependent upon the gas. Okay. Now for neutron, we are not going to do a very big thing here, right? For neutron, it's like you will be like, hey, something different. See, most simple because not that much is in your detail. You just have to, in your exam, in your syllabus, you just have to remember one single reaction here that I'll tell you. First thing is you should remember that this neutron actually has zero charge. And this neutron has mass nearly same of mass of proton. And we will discuss the models also today, Thomson model, Rutherford model. So these models, when Thomson was making his model, when Rutherford was making his model, they had no idea that neutron exists. Neutron discovery was after Thomson model, right? So that you need to remember that Rutherford model was there in 1920 and neutron was discovered in 1932. So that's why in Rutherford model you will have no talk about neutron. You will talk about electron, proton. After Rutherford discovered the structure of atom by Rutherford model, then we will put neutron into it, right? Okay, so how we did it? So it was a very simple thing that beam of alpha particles. What are alpha particles? That is helium-2 positive. From helium you take out 2 electrons, that is your alpha particle. Alpha particles are bombarded, is incident on the beryllium, and a very new type of particle was ejected, that is your neutron. Now, next question is, ma'am, why he used beryllium? Can't he use any other metal? Can't we have neutron out after bombarding alpha particle on any other element? It's possible. But how Chadwick did is, he did it with beryllium, right? So that's why I'm telling you about beryllium. Right? It's possible to do it with other metals also. After that, scientists did it, but we are only talking about Chadwick discovery here. The first time how neutron was discovered, right? Okay, so mass is almost equal to mass of proton, that is this much, and charge is going to be 0, right? Okay, so these were the 3 particles that you have. This is the whole thing that you have to remember. This is the absolute charge. This is the absolute mass. Relative charge, we take it as -1, +1, 0. Relative mass of electron. See, electron is minus 31. This is minus 27. This is minus 27. So we take electron as almost negligible mass, that is 0. And proton and neutron, we take it as 1. That's why we say that mass of atom is equals to neutron plus proton, because we take that approximately electron mass is negligible. This we'll talk about later in this chapter, so don't worry about that, right? Now let me, okay, just tell me this. Wait a minute. Yes. Arey? Bhai Sahab. Don't tell me that. I don't know why it is not showing that. So this is a very important question. The E by M ratio of anode ray in comparison to cathode ray is very low, high, same or none. So answer, as you have seen also, it is very low. Now I'll tell you why it is very low. Right? See, E by M ratio of anode. They are saying in comparison to cathode rays. See, tell me which has more mass, anode or cathode? Obviously, electron has less mass than proton. So E by M ratio is inversely proportional to mass. Okay. If you have more is the mass, less will be E by M ratio for a constant charge. So we can say that if E mass is this, then E by M ratio of electron is be greater than E by M ratio of proton. So answer will be, for a node, it is going to be very, very low. Okay. Yes, everybody. Now, next is our two models, that is Thomson and Rutherford model of an atom. Let me know in the chat box if that is clearly clear to you or not. Guys, let me know in the chat box if that is clear to you or not. Everyone? Yes? So, now I will focus on the board, guys. Okay? So, Thomson model of an atom, Rutherford model of an atom. These are the two things that we are going to focus on. So, let's see this. See, Thomson model of an atom is very simple. It's like watermelon, right? So how many of you love watermelon, right? So what we eat? Do we eat the black seeds? No, we eat the red part of it, right? So similarly, here he discussed that just like you have watermelon in which you have red part all over the watermelon, and inside you have these small black seeds, right? Inside you have these small black seeds. So he said that this red part is nothing. That is your uniformly distributed positive charge, right? And these black seeds that you see, these are the electrons that are there, right? So he stated this model, right? Now, I'll also tell you in detail. He also stated that this is just like plum pudding model also, or it is also called watermelon or plum pudding model. For you guys, watermelon will be more easy to understand because see, I don't know if you have like ever eaten plum pudding or not, but that thing I'm sure that you have eaten watermelon, right? So for us Indians, watermelon is the good example, right? So now, if you talk about Thomson model, that was a good model, ma'am. Okay, so he said that what his merit was, he was able to tell that atom is electrically neutral, right? He said that the positive charge is equal to the negative charge in an atom, right? But there was this major drawback that lies in the Rutherford model, right? So I'll tell you that here, right? So let me just show you that. Okay. Okay. So if you see this here, guys, this is the model of Thomson. This is Thomson model. that this whole red part is, I know this is not looking like a watermelon, but let's just assume this is the kind of model that he gave, right? So that some red part is uniformly distributed, that is the positive side, and these seeds that you have here, these are like pearls that you have here, these are the electrons, right? So Rutherford was also doing the same experiment. Now I'll show you with the help of simulations what is the difference here, right? So if you see, when Rutherford was doing the model, he was like, I'll throw the alpha ray here, I'll see the traces, and this is the kind of thing that he observed, right? What is the kind of thing that he observed? If I say energy is maximum, let's say, see, you just need to firstly just don't get into I have to learn this. Just see what exactly is there, right? So what he observed is, he observed that some particles were going straight, some particles were deflecting, some particles were also bouncing back. I'll talk about this also. But if you talk about this particular same thing, alpha particles, how they are going. Here it is showing that it is going straight, but if you see now, they are like not exactly going straight. They will be little bit deflected here, like because they will find some hindrances in between, right? So alpha particle is positively charged. This whole thing is positively charged. So exactly it will not be like this, right? So it will be like, because this whole is positively charged, so they will feel some restrictions here. But it's not like they will go extremely straight. See, if you're like, you are walking in India, see, let's take an example of India, and this is showing that it is like USA or some Europe or some like country where population is very less. In India, we know that population is very high, right? Even if you're walking on a street, you can't say that I'll walk like eyes closed, I'm walking and I'll walk in a straight line, I will not collide with someone. Highest probabilities you will collide with like so many people, because there is so much population is there. And no matter you go to hill station, you go to a village, anywhere you go, there will be population there, right? Our population rate is very high, right? But if you are like, let's say you are in Paris, right? Population is very low there, right? So now you're going to Paris is still a tourist place. Let's say you're in Denmark, right? Whatever is your like country that you want to visit, just think about that, right? So now there in vlogs also you must have seen that the roads are empty only. Very rare people you will see there, right? So there, because it is empty, so you can walk in a straight line, like listening to some music, no worries. But now when you're in India, you'll be like walking like, oh, here, then here, you'll be like, oh my God, here, especially us girls, we are like, oh my God, what is happening, dude, right? We have to be like fully like careful, right? We'll be like, hey bro, like I need to go, right? So that's the same thing in Thomson and Rutherford model, right? Thomson said that there is no empty space here. He didn't talk about any empty space, right? So according to his model, if I am saying that Thomson model is correct, then on passing the alpha rays, they should be not passing in a straight line. This is actually a wrong simulation. It should be going like this. Like there will be some restrictions here. If you talk about Rutherford model, here when you pass the alpha rays is positively charged, right? Because Rutherford model will state that the protons are there in the nucleus, and nucleus is very small, right? That's why we can see that most of the space inside the atom is empty. That's why most of the particles are moving straight, right? So first observation. Now, firstly, let's talk about the Rutherford drawback. The drawback was that, what was the drawback, everybody? Everyone, what was the drawback? Ma'am, the drawback was that he was not able to explain the results of scattering experiment. He was not able to explain. Rutherford's like, if you are right, then tell me why when I pass alpha particles through the atom, why they are moving straight? This simulation is actually asking a question here. The question is that if alpha particles you pass here, it should be moving straight. It should be moving straight because this is what Rutherford has observed, that they should move straight. But the straightness, the emptiness does not apply to Rutherford model. So Rutherford model was ruled out here, that this is the incorrect model for sure, right? That's how we know that Rutherford had an incorrect model, because he was not able to explain that how come alpha particles are moving straight, right? Now Rutherford gave the experiment. I'll tell you what exactly he did in the experiment, right? So he did the experiment in 1909. Here no neutron was discovered till Rutherford experiment. Used as a source of polonium was used as a source of alpha particles. Alpha particles are positive particles, like you have helium, 2 positive ion, that is your alpha particle. So this is the experiment that he did. What he had is, he had this radioactive source from which alpha particles are going. He had this empty space here from which alpha particle is striking this gold foil. First question, why he chose gold foil? Because metals are highly malleable. Malleable means they can be drawn into very thin sheets. Now, gold is one of the highest malleable metal, right? That's why we used it. Second question is, ma'am, why we need so thin sheets? Because same thing, less atoms, more conclusions we can draw for it. More atoms, it will be messy to draw some conclusions and observations from it. So that's why lesser the thickness, less atoms will be there. More clarity will be there, right? So that's why very thin sheet we used, right? Now, this is the fluorescent screen. This is the fluorescent screen. Now, what happened here? This is passing here and this will strike the fluorescent screen. And now I will tell you what are the observations that you will see here. Okay? What are the different observations that you will see here? This is your alpha particle. Alpha particle will strike. Let's see what is happening here. So this is the atoms of gold foil in a zoomed in version, right? Now, why I have kept the traces here, so that you can understand what is the path. If I don't keep the traces, you won't be able to understand the path, okay? So that's why I have kept the traces. You can see this, the site is there, it's a very good site, right? Totally free it is, so you can use it to understand also, but I am showing you, so you don't need to do it again and again, right? So this is just to tell you the visualization of this. So now you will see most of the alpha particles are moving straight, right? So next observation is that some alpha particles are deflecting, and when they are deflecting, when they are very near to the nucleus, when they are near to the nucleus, when they are near to the nucleus, can you see near to the nucleus they are deflecting? Alpha particle is positively charged, nucleus is positively charged, alpha particle is positively charged. If it is getting repelled by something, that has to be positively charged as well. So he didn't define nucleus as such at that point. He just said that there is some very positive charge, very high, good positive charge in a very small area that is there inside the atom, right? Now question is why he said that it is a positive charge? Because alpha particles which are positive are getting deflected near to that. Why he said that it is a very small space, it carries a very small space in the atom? Because most of the alpha particles are going straight. That means most of the space inside the atom is empty. There is very minor space that has positive charge, but as soon as it goes, the alpha particle goes even near to it, it will start deflecting. Like this, it will go even near to it, it will start deflecting, it will start changing the path. Now, I don't know if you have seen now any bounce back atom. 1 in 20,000 will bounce back. That we have to wait. Okay, that's why we have to wait for that one. Yeah, this was the bouncing back, right? That was the atom that bounced back. Again, we have to wait. Because 1 out of 20,000 is bouncing back. Till now, because now it has to directly collide on this positive charge, which is called nucleus. After that, I can't see any other bouncing back. Let's see. No, all are deflecting and moving straight. So that's why most of it are moving straight, right? Some of it are deflecting and very rare are bouncing. Now this was the bouncing back, right? So very, very rare are bouncing back. That is 1 in 20,000, right? So now I'll tell you the theory part of it, right? So it is, so what you had here, right? This is, I showed you this, that most of the alpha particles are moving straight, some of them are deflecting, and very rare are actually bouncing back. So these are the three conclusions that we have, observations that we have. Now, from observation, what is the conclusion that we can draw? Observation 1 is, most of the alpha particle pass through gold foil. That means most of the space inside the atom is empty. Second is, a small fraction of alpha particles were deflected by small angle. Wait a minute. Is there something wrong here? Okay. Acha. Am I getting the same thing again and again? Am I stuck in a loop, guys? Yes, ma'am is stuck in a loop. Chal. No worries. I'll just tell you the conclusion myself because we don't have it now. But no worries, your ma'am is here. Chal. I'll tell you about all the observation and conclusion side by side, and some important part also I'll tell you here, right? And what about the homework? No issues. I don't know what just happened to this particular PPT here, right? So no issues, right? So if you see, this shows that it has empty space, okay? This has empty space. What about this one? It shows that some of the alpha particle deflected through small angles, or very few alpha particles were deflected by large angles. This clearly shows to us that inside the atom, you have a very small, dense, small and very dense. So this nucleus that we are talking about is very small and it is very dense, right? And it is positively charged. And it is positively charged. It's like you have a cricket stadium and inside it you have ball. That ball in front of a cricket stadium is very small. So that is your nucleus in front of the atom. And we also say that like radius of the nucleus, you can keep it as 10 raised power minus 15 meter, right? And radius of atom, you can take it as 10 raised power minus 10 meter. So when you take the ratio, radius of atom is 10 raised power 5 times of radius of nucleus, right? So when you take the ratio, right, by cross multiplying, this will be the answer here. Here we can understand that actually it is 10 raised to power 5 times bigger than the nucleus, which is a very big deal, right? And if someone asks you, ma'am, who discovered, if someone asks you what Rutherford discovered nucleus, right? He had no idea about neutron. He said that, what he said, I'll just show you because the PPT is not there. So I'll just write it myself. He said that, very important thing, that this is the nucleus. He said that inside the nucleus you have proton and electrons are revolving around it. This was by Rutherford model, right? Now, what were the drawbacks of Rutherford model, right? Why again we need Bohr model now, right? What was the drawback of this Rutherford model? So the drawbacks of Rutherford model was, first was Maxwell theory. Okay, so Maxwell theory said that if you're talking about like this electron that is rotating, you are saying that this is proton, right? This is the electron that is rotating in a circular orbit. If you're saying that, even if we keep the speed same, the direction is changing at every point. Direction is changing, that means velocity is changing, right? So that means this particular particle is accelerated. And if you have any charge particle that is accelerated, any charge particle, any charge particle, charge particle which is accelerated, will radiate energy, will radiate energy. Can you tell me what is this radiate energy? That means it will lose energy. And you know what will happen here? It will radiate, this is the proton, it will radiate energy like this, like this, like this. And eventually in this spiral path, it is going to fall into the nucleus. That means according to Maxwell, if this is the model, if this model is correct, then atom should not be stable. That means Rutherford was not able to explain why this atom is stable. Because we are stable, you are stable, this pen is stable, it is not breaking like this, right? So why atom is stable? Why we are stable? Because clearly atom is stable. But because of this theory, atom will not be stable, right? So how come it is not traveling in a spiral path, right? Second is, he did not give any information about electronic distribution. Electronic distribution. Electronic distribution. He gave no conclusion of what is electronic, what is this electronic distribution. He had no idea about it, right? So that is it. So we know that in when you will study electronic configuration, that is the electronic distribution. With Rutherford was like electrons are rotating. How they are rotating? How many electrons are rotating? What is the distance from the nucleus? He had no idea about it, right? So that's why we say that this model is also failed now, right? So we are studying something, then we are failing it. Acha, now I'll give you one homework question. Just give me a second, right? I'll just write it myself only. Okay? So it is going to be everybody. Wait a minute. Wait a minute. So I'll just give you one. So many beautiful slides were there, but no issues. It's okay, guys. It's okay. Sure. Let me just see a question. Okay. Now you have to tell me two homework questions I am writing for you here, right? Two homework questions I am writing for you here. First question here, this is the second question here. First one is, wait a minute, first one is, electric discharge through gases could be observed. Electric discharge through gases could be, that's why I take PPTs. I hate my handwriting. Could be observed properly under, I'm writing it here. Options I'm not writing, guys. You write it. Dash pressure and dash voltage. Okay. So this is the first question. And second one is, this is, let's see how many of you are able to, how many of you are able to tell me this. Nucleons are what? Option A, electron plus proton. Option B, electron plus neutron. Option C, electron plus neutron plus proton. Option D, you have electron plus neutron plus proton. So what are the nucleons? Okay, so you need to tell me in the chat box, in the comment section actually, that which of the following is the correct answer. This is your homework, question number 1, and this is question number 2. Okay guys, so that's it for today, and very important information for all the students here, right? If you are off from the pro batch, then students, this information is for you. You can see that NEET Pro Courses right now, there is off going on at, if you're like preparing for NEET 2026, then the off is 10,000. If you're preparing for NEET 2027, then the off is 20,000. So in this is for all the students who don't want to travel, but they want to sit at their home, but someone guiding them, someone there 24/7 for them. So in this particular batch, what you will have is, you will have like proper person, mentor, who is looking at you when you, like for example, I am teaching you, okay? So in the batch, I am teaching you, and very limited students will be there in one batch, so that we can take care of individual students, right? So in that, what will happen, for example, you are learning, right? So you are learning, you are getting distracted, you are not looking, you're like sleeping in between. The mentor will be like, what you are doing? Why not studying? It's the same thing that happens in the classes, right? In the offline classes, right? So you will be very attentive. You will not be, see, if you're someone who is getting distracted, who is like using Instagram in between Diksha Ma'am is teaching, so this particular batch is for you guys, right? Because in this batch, there is no chance of getting distracted. You are solving the questions and you're getting doubts again and again. So 24/7 doubt solving facility will be provided to you. So these are the major things that will be provided to you. Other thing is live sessions will be there, where we can also see that what exactly you are doing. Your video, your mic will be on. Regular parent teacher meeting will be there. Your report card analysis will be there. Rest of the things, mock test, test series, modules, everything will be provided to you. QR cards, everything is there in this particular batch. You don't need to purchase any batch if you're purchasing the pro batch. Be it QR cards like this, these are the QR cards that you have, anything that you have, right? This is what you need, right? So, or even you will be guided personally here, right? You will have a dedicated counselor, right, which will actually take care of you, like what are the problems, the things that you waste time on, what is the strategy, like you have backlogs, how to complete that, everything will be done in the class, given individualistic learning experience to every student out there, right? So this batch is for you guys, right? So guys, that's it for today. Okay, chalo. Okay then students, now I'll take your leave and see you all in the next class, because in the next class we are going to do EM waves, we are going to do black body radiations, then we will do EM waves, black body radiations, Planck's quantum theory, photoelectric effect, right? The things that are going to move, that we need. So it's like whenever you're preparing for a war, you need to have all the weapons, right? So our weapons are these that I just talked about. So before Bohr atomic model, we have to learn all these things. So next, we are left with only 2 models, but in these 2 models, you will have too many rules, too many formulas. So be prepared for that, right? So everybody, let me know in the chat box, in the comment section, how was the class? And I'm waiting for you guys to do the homework. And where is the homework? This is the homework. Okay, so this is your homework, and I am waiting for you guys to write it down in the comment section, what is the answer for both of these things, right? Okay then guys, bye bye, take care, see you all in the next lecture, bye bye.